Quantum can seem like a pretty scary word. Quantum entanglement, quantum chromodynamics, quantum electrodynamics. These all seem to say the same thing. This is a very complicated sciencey idea, which you won't understand, so don't even try. All quantum actually means is the study of things at an atomic or subatomic level. And what makes quantum things a bit tricky is that when you get down to that kind of size, you have a whole new set of rules for how physics works. So that impression of complexity isn't entirely inaccurate. Nobel Prize-winning physicist Richard Feynman once said that the reason his students didn't understand quantum mechanics is that he didn't either, and he wasn't joking. But not understanding the deep physics doesn't mean that you can't grasp the underlying concepts, and it's with that in mind that we're going to talk about quantum computing. In regular computing, the processing and memory component of the computer takes the form of an integrated circuit. Information on this circuit, or chip, is coded in a unit known as bits, and bits make up all larger units. The word is actually a contraction of the phrase binary digit, and that's exactly what it is. Each bit is either a 1 or a 0, and these are the building blocks of computing. In quantum computing, however, the chip is actually an atom, known as a quantum bit, or qubit. Quantum mechanics allows the qubit to be both a 0 and a 1 at the same time. This means that qubits can hold twice as much information as a regular computer bit, and that their computing power increases exponentially as you add more of them. Now that's a fairly mind-bending concept. Yes, qubits are both a 0 and a 1 at the same time. This is called quantum superpositioning, and even the most seasoned scientists have trouble getting their heads around the idea, so don't worry about it too much. Think of it like this. A water particle can be in several different states: ice, water, steam, but it can only be one at a time. A qubit is like a water particle that can be all three of those things simultaneously. So because qubits represent a significant increase in computing power, when quantum computing becomes more developed, scientists hypothesize that they will be able to process problems more than 1,000,000 times faster than traditional computers. This means huge leaps forward in areas like complex system modeling, data analytics, aviation, self-driving cars, and cryptography. That last one is particularly interesting because it means that lots of our current encryption techniques could be rendered obsolete, which is why the NSA is pretty worried about it, making hefty investments in the technology. But that level of processing power is still a way off yet. The nature of how quantum computing works makes them expensive, fragile, and a little bit unreliable, for now at least. So progress is slow. In 2009, researchers at Yale University made the first solid-state quantum computer, which contained 2 qubits. And Google and NASA followed suit in 2017, releasing the D-Wave 2000Q, containing 2,048 qubits. When tested against a traditional server, the D-Wave outperformed its counterpart by factors of between 1,000 and 10,000. Impressive, but scientists generally agree that a fully functional quantum computer would have 1,000,000 qubits working away. So clearly, we're just getting started. Realistically, it's unlikely that we'll ever see this technology in our laptops or phones. A quantum computer has to be called almost absolute zero, and on top of that, they can't experience any interference whatsoever. That means no electromagnetic disruption, no blackbody radiation, which includes the infrared light humans give off. It can't even be observed by a stray photon. So that means absolute darkness. The result of all this is that right now, quantum computers are a little larger than you would expect for a computer made of a handful of atoms. D-Wave, for example, is a bit bigger than the average garden shed, but that's still a fraction of the space taken up by the supercomputers they'd be replacing. And while for supercomputers, dramatic increases in processing power mean dramatic increases in size, in quantum computing, that isn't the case. We said that we'd expect a fully functional quantum computer to have 1,000,000 qubits, right? So that's the size of 1,000,000 atoms. Well, for scale, a grain of sand contains just over 31 sextillion atoms. That's sextillion with 21 zeros, enough to fit our 1,000,000 qubit computer 31 quadrillion times over. So let's not worry too much about the space issue. Even though we've really only scratched the surface here, it's good to have a handle on the basics of what quantum computing means, because it's a massively exciting topic at the very cutting edge of human scientific understanding and achievement, which when fully realized could have the capacity to change our lives in far-reaching and as yet unknown ways.